Light would need more than 46 billion years to reach the edge of the universe, but we'll take you there in just 25 minutes. This isn't magic. It's the result of centuries of cosmology research, combining data from the most powerful telescopes with ultra-precise 3D simulations of space. On this journey, you'll witness the very first light after the Big Bang, glide past vast clusters of galaxies stretching like continents across the cosmic ocean, and travel to the farthest reaches where space-time becomes so strange that our familiar laws of physics begin to break down. And if you don't want to miss any future voyages, whether it's exploring supermassive black holes, unlocking the secrets of dark energy, or glimpsing the far future of the cosmos, hit like and subscribe now. With a single click, you'll become part of our exploration crew, pushing beyond the boundaries of human knowledge. When people hear edge of the universe, they often imagine a gigantic wall at the end of space, a physical barrier where the cosmos stops. But in reality, the edge of the universe isn't a thing or a structure. It's the limit of what we can observe. More precisely, it's the farthest distance from which light, or any form of electromagnetic radiation, has had time to reach Earth since the universe formed about 13.8 billion years ago. This distance is called the radius of the observable universe. Here's the surprising part. Astronomers measure this radius not as 13.8 billion light-years, but about 46.5 billion light-years. The reason comes down to a key concept in modern cosmology, the expansion of space. Why is 46.5 billion light-years larger than the age of the universe? Right after the Big Bang, the universe began expanding, and it has never stopped. As light from distant galaxies travels toward us, the space between us and those galaxies is also stretching. This means that the actual distance to those early galaxies today has ballooned far beyond the distance the light originally traveled. So even though the light has been traveling for 13.8 billion years, the present-day distance to the edge of the observable universe is about 46.5 billion light-years. How do we measure the edge of the universe? Two of the most important tools are ESA's Planck satellite, measures the cosmic microwave background, CMB, the ancient afterglow, from when the universe was only about 380,000 years old. The James Webb Space Telescope, JWST, observes galaxies as they appeared just a few hundred million years after the Big Bang, confirming our models of cosmic expansion. The CMB is essentially the oldest photograph we have of the universe. It marks the moment when matter and radiation separated, making the universe transparent and allowing light to travel freely through space for the first time. Beyond the edge, the unobservable universe. Beyond the edge of the observable universe lies the unobservable universe, regions of space from which light or any signal will never reach us, because space there is expanding faster than the speed of light. Einstein's physics tells us that nothing can move through space faster than light, but space itself can expand at any speed. This means there may be countless galaxies, stars, and planets beyond our cosmic horizon, but according to our current understanding of physics, we will never be able to detect them. A helpful metaphor. Think of the edge of the universe like the horizon at sea. You know there's more ocean beyond it, but you can't see past it because of the limits of your vision. And just as the horizon moves as you move forward, the edge of the observable universe also shifts over time. It's not a wall. It's a moving boundary defined by what light has had time to reach us. 2. A 25-minute journey to the edge of the universe, the scientific view. First, let's be clear. No object with mass can travel at or faster than the speed of light in a vacuum, a limit firmly established by Einstein's theory of special relativity. That means physically reaching the edge of the universe in 25 minutes is impossible. However, popular science and modern simulation technology can compress billions of years of cosmic history into a 25-minute experience, allowing us to see things that human feet could never touch. 2.1. The simulated journey. Principle. Using observational data from space telescopes such as Hubble and James Webb, combined with standard cosmological models like lambda CDM, which describes a universe made of dark matter, dark energy, and ordinary matter. The core idea is that light from distant objects is a message from the past. When we observe a galaxy 10 billion light-years away, we're seeing it as it was 10 billion years ago. Process. Astronomers collect light data from millions of galaxies at different distances. Each distance corresponds to a time slice in the history of the universe. By stitching these slices together, scientists build a 3D map of cosmic history. Gaps in the data are filled using numerical simulations based on physical laws and galaxy distribution statistics. Experience. Viewers launch from Earth, leave the solar system, pass through the Milky Way, exit the local group, and travel beyond massive superclusters like Laniakea. The journey ends at the cosmic microwave background, CMB, the edge of the observable universe. This is the oldest light we can detect, emitted when the universe was just 380,000 years old. Debate. Some scientists argue that such simulations can never be fully accurate because unobserved regions rely on assumptions. For example, we cannot know for sure whether galaxy structures on the far side of the observable universe match what we see here. Supporters counter that simulations are the most powerful educational tool available, helping the public visualize the immense scale and structure of the cosmos. 2.2. Fast-forwarding through time. Concept. If each second of the experience represents hundreds of millions of real years, then in just 25 minutes, 1,500 seconds, we can watch the entire 13.8 billion year history of the universe. Key moments. 0, 10 superscript 3 superscript 2 seconds. Cosmic inflation. The universe's size increases by a factor of billions in a fraction of a second. 380,000 years after the Big Bang. The universe becomes transparent, and the CMB is released. 100 million 1 billion years. The first stars, population 3, form, followed by the birth of galaxies. Today, the universe contains hundreds of billions of galaxies and is expanding at an accelerating rate due to dark energy. Debate. Some educators warn that compressing time may cause the public to think expansion happened at a constant rate, when in reality it slowed under the influence of gravity, then sped up again as dark energy took over. Many science communicators respond that the priority is to spark curiosity with striking visuals. Detailed explanations of physics can come afterward. 2.3. Virtual reality (VR) technology. Principle. VR recreates the 3D structure of the universe using real astronomical data. Users wear a VR headset and fly through space like an invisible astronaut. Examples. Universe Sandbox and Space Engine let users explore from the surface of planets to the largest galaxy superclusters. NASA has also developed VR models that simulate a trip to the edge of the observable universe. Strengths. VR creates a powerful sense of presence. You can glide past galaxy clusters, see massive walls of superclusters stretching hundreds of millions of light-years, or drift through vast, pitch-black cosmic voids where almost nothing exists. Debate. Some experts caution that VR can blur the line between entertainment and scientific accuracy, since many details in these models are based on assumptions about unobserved regions. Still, most scientists agree VR is an extraordinary way to inspire people and bring space science closer than ever before. Light bulb scientific takeaway. A 25-minute trip to the edge of the universe is not a physical voyage. It's a journey of understanding. It's where observational data, mathematical models, and visual technology merge to expand our view to the farthest limits we can know. It also reminds us that all current cosmological knowledge is provisional and could change when science turns the page to its next chapter. 3. From the Big Bang to the edge of the universe, a journey through time and light. Imagine standing on humanity's most extraordinary launch pad, not a spacecraft, but the combined power of imagination and science. We won't be flying to a distant point in space. Instead, we'll be diving backward through 13.8 billion years of cosmic history, returning to the moment the universe was born. This journey is unlike any you've heard before. We will touch the Planck moment when every known law of physics completely breaks down. Witness cosmic inflation, a burst of expansion faster than the speed of light, enlarging the universe from subatomic size to a massive sphere in a fraction of a second. Pass through the opaque era, when light was trapped in a searing plasma ocean, until protons and electrons combined into atoms and the first light burst free, leaving behind the oldest photograph we have, the cosmic microwave background (CMB). Watch the birth of stars and galaxies, from the first giant stars to the cosmic web of galaxies stretching across space. Enter the era of dark energy, when the expansion of the universe accelerates, pushing distant galaxies forever beyond our reach. And all of this leads to a boundary that seems impossible to cross. The edge of the observable universe, where light has taken over 46 billion years to reach us, yet is still just a tiny window into the infinite ocean of reality. The earliest moments, from the Planck era to inflation. 10 superscript 3, 10 superscript 3 seconds, Planck era pre-inflation. Physics has not yet unified quantum mechanics with gravity, so this is the blank space of knowledge. Energy density was extreme, and all fundamental forces may have been unified. 10 superscript 3, 10 superscript 3 superscript 2 seconds, cosmic inflation. Space expanded at an incredible rate, magnifying the universe by many orders of magnitude in less than a blink. Tiny quantum fluctuations were stretched into large-scale density ripples, the seeds of galaxies. Why it matters. Inflation explains why the universe appears uniform and flat on large scales, and predicts the nearly scale-invariant pattern of fluctuations observed in the CMB. From the particle soup to stable building blocks. 10 superscript 1 superscript 2 seconds, electroweak symmetry breaking. W and Z bosons gained mass, and the fundamental forces separated into the ones we know today. 10 seconds, quark-hadron transition. Quarks became confined inside protons and neutrons. The universe shifted from a quark-gluon plasma to stable hadrons. 1 second, neutrinos decoupled from matter, and the universe entered the radiation-dominated era. Big Bang nucleosynthesis, BBN 3 to 20 minutes. Temperatures dropped enough for protons and neutrons to fuse into light nuclei. 75% hydrogen, by mass, 25% helium-4, and traces of deuterium, helium-3, and lithium-7. Why it matters. These elemental abundances are a cornerstone test of cosmological theory, constraining the total number of baryons in the universe. The opaque era, 20 minutes 380,000 years. The universe was a charged plasma. Photons scattered constantly off free electrons, Thomson scattering, so light could not travel freely. Meanwhile, the density ripples from inflation began to grow under gravity. Recombination and the oldest picture, CMB, 380,000 years. Temperatures cooled to 3,000 K. Protons and electrons combined into neutral hydrogen. Photons were freed from constant scattering. This ancient light is what we now see as the cosmic microwave background. The CMB contains faint patterns in density, only 1 part in 100,000. The original blueprint for large-scale structure. Why it matters. The angular power spectrum of the CMB, its acoustic peaks, pins down key cosmological parameters. Near-flat geometry, dark matter content, baryon density, and traces of dark energy. The Dark Ages, 0.38, 0.1 billion years. No stars or quasars yet. Neutral hydrogen absorbed ultraviolet light, leaving the large-scale sky dark. In the background, gravity, especially from cold dark matter, was silently pulling matter into halos, the future scaffolding for galaxies. Cosmic dawn and reionization, 0.11 billion years. The first generation of stars, population 3, ignited hot, massive, and short-lived, creating the first heavy elements. Ultraviolet light from these stars and quasars ionized the neutral hydrogen, marking the epoch of reionization, completed by 1 billion years. Why it matters. We detect signatures of reionization through CMB polarization and the Lyman alpha absorption features in quasar spectra. Structure formation, 1 to 10 billion years. Galaxies, galaxy clusters, superclusters, and the cosmic web formed from the original ripples, growing under Newton-Einstein gravity in an expanding spacetime. The cosmic star formation rate peaked around redshift Z2, 3.5 billion years after the Big Bang, and then declined as gas supplies dwindled and feedback from supernovae and quasars took effect. Supermassive black holes grew in galaxy centers, shining as quasars. Baryon acoustic oscillations, BAO, left a standard ruler of 150 mpc in the galaxy distribution, letting us measure the expansion history of the universe. Dark energy era and the present, 13.8 billion years. About 5 to 6 billion years ago, dark energy overtook matter, causing the expansion to accelerate. Today's universe is roughly 5% ordinary matter, 27% dark matter, and 70% dark energy. Observable universe radius, 46 plus billion light-years. Moving. Cosmic event horizon. A limit beyond which light emitted today will never reach us due to accelerated expansion, implying a future in which more and more galaxies slip beyond causal contact. Why it matters? Evidence for acceleration comes from type Ia supernovae (BAO) and the CMB, together forming a consistent picture of dark energy in the lambda CDM model. Why the observable edge keeps moving. Light from distant regions continues to arrive as time passes. Meanwhile, cosmic expansion increases their present-day distance. As a result, the moving radius of the observable universe grows over time. However, due to accelerated expansion, there are regions whose light, emitted from now onward, will never reach us. Open questions and ongoing debates. Origin of inflation. What was the inflaton field? How did inflation end? Nature of dark matter and dark energy. Still black boxes in our models. Hubble tension. Different measurements of H, local versus CMB-based, disagree slightly, potentially hinting at new physics. Early massive galaxies. Discoveries of unexpectedly large, early galaxies challenge galaxy formation models. Connecting back to the edge. The edge is not a physical wall. It's the limit set by the finite age of the universe and the finite speed of light in an expanding space. Reaching the edge in 25 minutes is really about compressing the story of cosmic history. From the CMB, 380,000 years after the Big Bang, through cosmic dawn, reionization, the cosmic web, and the dark energy era, into one immersive journey that lets us understand, not physically travel. 4. Scientific and philosophical significance. In the previous section, we traced the cosmic timeline, from quantum fluctuations amplified during inflation, through the CMB at 380,000 years, to the cosmic web of galaxies and the current era dominated by dark energy. The temporary endpoint of that journey is the edge of the observable universe, a limit set by the finite age of the universe and the finite speed of light. From this point, two layers of meaning emerge. Empirical science, how we test our cosmological models. Philosophy of knowledge, what the limits of human understanding are. Scientific meaning, the edge as a cosmic laboratory. The pillars of observation. The edge of the observable universe provides, directly or indirectly, key measurements for testing lambda CDM, lambda, cold dark matter. The standard model of cosmology. CMB, cosmic microwave background, the anisotropy spectrum, and acoustic peaks yield estimates of the universe's age, baryon density, dark matter density, near-flat spatial curvature, and the primordial density fluctuations, 1-0. BAO, baryon acoustic oscillations leave a standard ruler in the distribution of galaxies, helping map the expansion history and cross-check CMB results. Type Ia supernovae serve as standard candles for deep distance measurements, revealing the accelerated expansion, the main evidence for dark energy. Weak gravitational lensing / large-scale structure. Track how matter, especially cold dark matter, distorts the shapes of background galaxies, testing the growth of structure over time. How the measurements lock in lambda CDM. The strength lies not in any single dataset, but in their mutual agreement. When CMB, BAO, and type Ia supernovae all point to the same set of parameters, roughly 5% normal matter, 25 to 27% dark matter, 68 to 70% dark energy, and near-zero curvature, we have a robust composite picture. Any significant mismatch between these pillars immediately signals either new physics or systematic errors in the data. The edge as a clock and ruler. The particle horizon, a moving radius of 46 plus billion light-years, defines the ultimate limit of what we can currently observe. The event horizon in an accelerating universe tells us that some regions of space, even if emitting light today, will never be causally connected to us in the future. Both horizons are geometric constraints, Any alternative cosmological model, e.g. modified gravity, must reproduce these observational boundaries. Open tests and tensions. Hubble tension, H local measurements versus CMB inferred values differ. Is this due to measurement bias or new physics? Early galaxy maturity. Massive galaxies at high redshift challenge standard star formation and feedback models, suggesting refinements in cooling, dust, and black hole feedback mechanisms. Nature of dark energy. Is it a cosmological constant, W equals -1, or a dynamic field, W, Z, changing over time? Pushing the observational edge deeper can help decide. Primordial non-Gaussianity/isotropy tests. Even tiny deviations from Gaussianity or isotropy in the CMB could be signatures of inflation-era physics. Methodological limits. Cosmic variance. On the largest scales, we have only one universe to measure. There is no way to repeat the experiment. Some uncertainty is irreducible. Selection bias and Bayesian inference. We generalize from the observable portion, 46 billion Ly radius, to the whole. Requiring assumptions like the Copernican principle, we are not in a special location. Every conclusion must carry an explicit confidence level. Philosophical meaning. The horizons of human knowledge. Limits of knowledge and the incompleteness of our maps. The observable edge is a constant reminder that the map is never the territory. Even as our data become more precise, anything beyond the horizon remains unknowable under current laws of physics. Science here is both humble and powerful, building the best conditional models, always open to revision. The extended Copernican principle. The assumption that we have no privileged position allows us to extrapolate from what we see to the whole universe. Philosophically, this is not an a priori truth but a reasonable working belief, one that has held up so far, but could be overturned by evidence of anisotropy or inhomogeneity. The anthropic principle and fine-tuning of parameters. Why do parameters like dark energy density or the fluctuation spectrum fall into the narrow range that allows structure and life? Some anthropic arguments say we observe this universe because it permits observers like us. This is not a physical solution, but a selection effect framework within a larger possibility space, potentially including a multiverse. Causality and the meaning of an isolated future. The event horizon paints a sobering picture. Over cosmic time, most galaxies will slip beyond causal contact with us. Philosophy of science must then ask, what is the meaning of knowledge when the domain of empirical verification shrinks with time? Reality and models. Modern cosmology exemplifies structural realism. We may never fully grasp the ultimate substance of reality, but we can describe the relationships among measurable quantities. Distance, brightness, redshift, structure distribution. Lambda CDM's success shows that knowing the structure is enough to make accurate predictions and manage uncertainty. Conclusion, an invitation to explore. 25 minutes may not be enough to truly fly to the edge of the universe aboard a real spacecraft, but it's more than enough to compress 13.8 billion years of cosmic history into a vivid and mesmerizing journey. In that short span, you'll witness the universe's most extraordinary moments, from the birth of matter and energy in the Big Bang, to the first light breaking through the primordial fog, to the first galaxies crystallizing out of chaos, and finally to the relentless expansion of spacetime pushing the visible edge ever farther from our reach. Each second of this trip represents hundreds of millions of real years, an era in which stars are born, shine brilliantly, and fade away, leaving behind the elements that will seed the next generation of stars and planets. You'll watch colossal clouds of gas collapse into galaxies, supernovae scattering gold and carbon across the cosmos, and supermassive black holes quietly shaping the rhythms of galactic life. But this is more than just a cosmic sightseeing tour. It's an invitation to understand, to realize that the faint light you see on the screen is a message sent billions of years ago, living proof of physical laws we've only begun to grasp. Every pixel of light holds a story, and every story is a piece of the grand puzzle we call the universe. So join the journey. Keep your eyes wide open, your mind even wider, and let science guide you across the farthest frontiers of human understanding. And if you'd like to keep traveling through the darkness of dark matter to the final days of the cosmos, don't forget to hit like and subscribe. One small click, but your ticket to never missing a single step on the endless path of discovery.